example, find the volume of the solid obtained by rotating about the x-axis, the region under the curve y equals square root of x from 0 to 1. So I am going to start these problems a lot like the area problems. I need a picture of my region that I'm starting with. So let's see. They tell me my equation is y equals the square root of x, and I'm going from 0 to 1 here. So let's draw that graph, and I'm only interested in the part between 0 and 1. And this is the square root of x graph, so you're going to graph it up like this. Okay? And it continues on here. You want to know that? So this is my region right here. Maybe I'll color it in blue for you. This is my region that they're talking about. And I want to rotate this region about the x-axis. So what am I doing? I'm rotating this region around this x-axis. You should get a solid, so you're getting something three-dimensional. Okay? So I know these things are kind of hard to picture, and I'm going to help us a little bit later. I'll use a program for that. But imagine that this blue part comes off of the board and rotates around. So it looks like you're getting a bowl-shaped object, okay? You're bringing this out of the board, it's rotating around and down and to the back of the board as well. Okay, so let me try to sketch for you this solid that we obtain by rotating it. So we're gonna get 0 to 1. You're gonna get this kind of, it cuts off here, and this like bowl-shaped object. So what I need to do, if I'm going to find the volume, I said that integral depends on our cross-sectional area. So what I want to do is I want to take a slice of this this object here. So let me do that. Let me do that here in this picture, the first picture. I want to take out a slice of this, like a chunk of my solid. Remember what I do, I'm slicing it like a loaf of bread, slicing it, so I'm taking this rectangular strip and rotating it around. And so when you rotate this around, what are you gonna get? It rotates around, so it's solid around. You're gonna get this flat disc. Okay, imagine you cut the bowl in the middle, you'll have a flat disc. It's a filled-in bowl, which is what we're assuming. Imagine there's no hole in it to hold anything. So this is my cross-sectional area here. This represents a disc here. Or another way to think about a disk is it's a circular cylinder with a short height. If you want to think about it like that. So I can find the area of this, A of x, here, A of x. We said pi r squared is the area. And now I just got to think about my radius in terms of the picture. Okay. So I've highlighted the whole disk, but the radius is just half of the diameter. So it's just the top half here. It's just this top half here, and that distance is y. But y depends on your function. At different places, y is bigger and y is smaller. So that y is really represented by this function here, which was the square root of x. So that is your r. r here is y, but that's really square root of x. Okay, so I'm getting pi times the square root of x squared, or just pi x. So I'm ready to set up my integral for volume. The volume, it's the integral of, it was a of x, so that's this thing right here, pi x. So pi x dx. And now I've got to think about my bounds. What was my range on my x values in my picture? What was my smallest x value I had?
0.
0 was my largest.
1.
1. So it goes from 0 to 1. Okay. And then we just integrate, so this is going to be pi x squared over 2 from 0 to 1. So it looks like pi over 2 is my answer for this volume. Okay. Any questions right now? What we've done?
So the reason you did the pi r squared on the AX is because it's a cylinder, right?
It's a cylinder, it's a circular cylinder, and so the A of x is the area of my base, which is a circle, so that's why it's pi r squared.
So you don't have to worry about the height.
You don't have to worry about the height. The height is, it's hidden by this dx here in the integral. Because you're assuming that you're taking like a small width slice there, and so that's where the height comes in, yeah.